Well, we might as well start, seeing it's up fast. So we're just going to talk a little bit about linear programming, and then we essentially finished with the whole syllabus on optimization. Okay, there's been a bit of talk. Ah, good. Yes, so updating DWSim works. Yeah, because I updated my DWSim before I started setting up the optimization assignment. And I've got version 6.6, which is the latest one. Oh, good. Josh, thanks. Okay, good. Right, so we're just going to be doing a little bit about linear programming, and that's it. That's the end of the optimization syllabus, and we can go on to we can essentially go on to the TUT while we're busy in advance of the TUT session. Okay, so let's have a look at this. A typical example of linear processing is when you've got the variables are flow rates of chemicals. So a reactor produces two products, A and B, and these products are separated in a distillation column. Reactor conditions can be changed in order to change the ratio of A and B, but the sum of their production rates may not exceed 2 tons per day. Similarly, the distillation column can only be operated with a constraint that the rate of B minus A cannot exceed 1 ton per day. B is 3 times more valuable than A, and the optimization problem is what's the optimum production flow rates of A and B. So yeah, so you can see that the variables are the flow rates of A and B, and that is typical of all these linear programming problems. Now I've got to figure out how to. Here we go. So the objective function, let's go back, is where you look at the objective function. You can see from this. Yes, you can see my pointer now. B is 3 times more valuable than A. So if you look at profit, that you want to maximize profit, you've got to take the flow rate of B and multiply it by 3 compared to the flow rate of A, which you can just take as, there we go. If we multiply the flow rate of B by 3, it affects the profit 3 times more than that affects the profit of A. It doesn't really matter if you multiply this entire function by a constant. It doesn't really matter. It's the shape of that objective function will still be the same. So it doesn't matter what the absolute value of A is and the absolute value of B. It's the ratio that's important because it's only that affects the shape of the objective function. Okay, so then the constraints were that the reactor can produce only 2 tons per day, the sum of their production rates. So if x1 is the production rate of A and x2 is the production rate of B, that must be less than or equal to 2. And then on the distillation column, no, that's not a notification for us. Then on the distillation column, there we've got minus x1 plus x2 must be greater than or equal to 1. How is flow rate used to calculate profit? So I went through that a bit quickly. Let's go back to how it's phrased. B is 3 times more valuable than A. That's all the information you need for the objective function. So if you're producing 1 ton of B, it influences the objective function 3 times more than A. If you make 1 ton of B, you'll make 3 times more profit than if you make 1 ton of A. And that's how we're going to, that's how this objective function gets phrased. The profit, for whatever the function, whatever flow rate of A is, that's x1, whatever flow rate of B is, it makes 3 times more profit. That's all it is. It's the ratio 3 to 1, the multiplier of x1, and that's it. Okay, so we've done the reactor can produce only 2 tons, whether it's A or B. So the sum of the production of A and the sum of and the production of B must be less than or equal to 2 tons per day. And then this is the calculation for the distillation column. So let's go back again. Distillation column can only be operated with the constraint that the rate of B, that's x2, minus the rate of A. So it's x2 minus x1 cannot exceed 1 ton per day. So it must be less than or equal to 1. And I think we've got it wrong here. It says greater than or equal to 1. So this should be less than or equal to 1. The flow rate of B minus the flow rate of A must be less than or equal to 1. Cannot exceed 1. And then the normal constraints, x1 is greater than 0 and x2 is greater than 0. And now you can plot the constraints on a graph, and that's what it looks like. So that's the one we did yesterday. Now this x1 plus x2 equals 1 is the equality sign, and then the greater than or equal to or less than or equal to, it must be less than or equal to so if x1 is small and x2, if x1 is a small value and x2 is a big value, then there will be a positive, then this will equal to positive value. Let me just see what is the value. There's 1. That is 1. If they're both equal to 1, then the objective function should be equal to 0. So this is not really making sense. I'm just trying to figure out which side is the constraint. If you look at this equation, which side is the constraint? So if x2 equals a half, that's along this line, and x1 equals 1, that's minus 1 plus a half, must be less than or, okay, that is less than 1. Yes, that's fine. So that this side of the line is okay. This side of the line is where this constraint is less than or equal to 1. Okay, So that's the sum of the two production rates must be less than or equal to 2 equals to, and this side of the line, let's say x2 equals a half, x1 equals 1, then we'll have 1.5 is less than or equal to 2, which is correct. That's in this white section. And of course, x1 is greater than 0 is going from this line to the right, and x2 is greater than 0 is going from this line upwards. So all of these things are correct. That this is the allowable region. Yeah, Angela.
Prof, the description says the rate of B minus A cannot exceed 1 ton per day, but then in the mathematical description in the constraints on the next page, then it says minus x1 plus x2 is bigger than 1. Shouldn't that be a smaller sign?
Yes,
that second one. Yeah, that one.
Yes.
Oh, okay.
No, that should be a smaller than 1. I did say that, but
okay,
my notes are wrong. But eventually we get it right in the mathematical formulation. I'll show you. Right. So these lines are showing what the objective function is. So if both of these things are 0, the objective function says x1 is 0, x2 is 0, then c, the objective function, is going to be 0. So there's a c equals 0 line running all along here. If x1 equals 1 and x2 equals minus a third, then we'll have plus 1 minus 3 times a third equals 1, minus 1 equals 0. So that's why this point over here also equals 0. So you can see, you can take any of these points, and if you evaluate x1 and x2 along that line, you will always get c equals 0. Similarly, let's start over here. This is x1 equals 0. x1 is 0. And x2 equals 1. Then c equals 3. So there you can see c equals 3, and that'll be the same anywhere along this line. You can see that all of these lines have a slope of 1/3, which comes from that 3 essentially. And because they've all got the same slope, that is showing. Remember, I was talking about thinking of this as a piece of paper, a plain sheet of paper, sheet of cardboard above the graph of x1 and x2, above these constraints. And these constraints are walls going up. That sheet of paper, that shows that the sheet of paper goes from a high over here, and perpendicular to these lines, that's the highest slope going downwards. And along these lines, the sheet of paper is level. So obviously, if this line is the highest part of that sheet of paper, number 4 would give the maximum profit, because this objective function is defined as profit. So you can actually go and evaluate all of these nodes, and you'll see, well, you can already see the objective function equals 5 where it crosses that point. It's equal to 3 where it crosses that point. It's equal to 0 when it crosses that point. And of course, you can also go and do the calculation over there, but you can already see the way that the slope works. It goes upwards towards that side. So that is going to be the optimum point. So you're going to make a half a ton per day of A, and you're going to make 1.5 tons per day of B. And that's going to be your best, your optimum profit. Okay, so now let's look at the analytical solution, how you write these in terms of a linear programming in terms of matrices. So x1 plus x2 must be less than or equal to 2. And what you can do then to say, if that must be less than or equal to 2, so you add x1 and x2, and let's say you get 1.5. That is less than or equal to 2. You can add a new variable called a slack variable, x3. So if x3 equals a half, it's taking up the slack. And then you can say that equals 2. So let me just repeat that again. If you've got the situation where x1 is equal to a half and x2 equals 1, then you can just make up a new variable called x3, which is equal to a half, and you've got a half plus 1 plus a half equals 2. Then you don't have to be encumbered by inequality signs. And you're going to define these slack variables that they are always going to be a number that is greater than 0. So this one was a half, for instance, as an example. It was a half. It was a positive variable, and therefore all variables. So we've already defined that production rates must be greater than 0, and this one is also greater than 0. Now let's have a look at this one. Here it's correctly written. The flow rate of, remember we had them greater than or equal to on the previous slide, which was wrong. So that says that the flow rate of B minus the flow rate of A must not exceed 1 in the distillation column. And so that's how it's written. And so you can still write it in the same way and use a new slack variable, x4, and then you can make that equal to 1. Okay, so how we choose x3. Oh, x3, right, this one. I thought it was multiplied by 3, which is the objective function. Okay, so x1 and x2 is less than or equal to 2 means that, okay, in that final example here, this example here, we found a solution against the constraint where you've got x1 equals a half and x2 equals 1.5. And when you've got x1 equals a half and x2 equals 1.5, then you find that it's equal to 2. It's against the constraint, because then the sum of these two is at the maximum flow rate that the reactor can produce. Okay, but it is possible, because this is less than or equal to, the reactor can also be operating at less than 2 tons per hour, 2 tons per day. So it is possible that a valid solution can be that x1 equals a half and x2 equals 1. That will be less than, that's 1.5, which is less than 2. So that is valid. But we don't want to work with inequalities. We want to work with equalities. So we just put in a new variable so that it takes up the slack. If there's 1.5 over here, there's still a half that can be taken up in production rate. So we take up that extra half a ton per day in production rate as a new variable called x3. So it's just a variable that we add in to make sure that instead of using a less than or equal to, we can use an equals to, because when we use equal to, we can use normal matrix arithmetic to go and solve these things. You get that? Let me just read Lisa's. Would it always somehow work out that the optimal point on a node or can it, for instance, if it was a quadratic objective function, have more possibilities? Yeah, if it's quadratic, then it's not linear programming, and then it is possible that you can have multiple. It's only with linear programming that you can be certain that your optimum will lie on a node. So if you've got a quadratic objective function, it is quite possible. Let me just go back to the graph. If you've got an objective function, then you can have, let me get to a nice pointer options and go back to pen. Then it is possible that your objective function, instead of those straight lines, it looks something like this. And therefore, it's not necessary, so you might have another one. I won't change. There's another contour that runs over there. So it may be that the optimum lies somewhere along a straight line, because your objective function is not linear, and essentially that's what's happening. That's what's happening if what you say is correct. It was a quadratic objective function. Then you have more possibilities. It's not just the nodes that are possibilities for an optima. Right, so we can write the. Oh yeah, no, we were still over here. Yeah. So similarly with the distillation column, we had x2 minus x1 must be constrained to 1 ton per day. We can have another slack variable that takes up the slack if that is less than 1, then we use x4 to make it equal to 1. So that's exactly the same. And now we can write the problem as a matrix equation. So here we've got x1, x2, x3, x4 0. The coefficient for x4 0 over here equals 2. And we've got the minus x1, so that this coefficient is minus 1. This coefficient is plus 1. There is no x3 in this equation, and this one's coefficient is 1 equals 1. And now we can write that we want to maximize the objective function, which is x1 plus 3x2. And essentially, you can also read in that those slack variables should not affect the objective function, so therefore their coefficients will be 0. So they're just not written. So you can see for x2 equals 1, then x1 and x4 equals 0. So if x2 equals 1, then x1 and x4 equals 0. That's the only way you're going to make it work, because remember, x1 and x4 have to be positive values, or 0. There's that constraint that they must be positive values or 0. So solving the first equation, x1 equals 1, f equals 3, it is a feasible solution, but not necessarily the optimum solution. The graphical solution suggests x1 is a half, x2 is 1.5. Substituting, we find that x3 equals 0. So if you put that value into these equations, you'll find that you can, if you put those two values into this equation, you can solve for x3, because now x1 and x2 are known, and you can solve for 3, and you'll find with both of these equations, this one and the second one over here, Let me go to another pointer. Pointer options. Let's go to the laser pointer. Right. So let's see what that is. A little confused with the degree of freedom. We have three equations. Oh, yes. If it's going to be an optimization problem, you have to have those degrees of freedom, because otherwise you wouldn't be able to. Otherwise, you can just solve exactly for x1 and x2. You've got to have the degree of freedom with the slack variables, because if you're optimizing, you must be able to change x1 and x2 according to the objective function. So if you only had two equations, then it's simply a linear equation, and you find x1 and x2 directly, and there's no optimization to be done. You need to have that degree of freedom so that you can maximize these two. All right, so where we find that optimum, we find that it's against the constraints, and because it's against the constraints, none of the slack variables has got a value. They're both equal to 0, and the value of the objective function equals 5. So in reality, it means we are operating at the constraints of both the reactor and the distillation column. So let's go back to that graph and see what that. Right, let's go backwards with it. I've got my ugly curved lines here. If this happened to be the maximum, the optimum, we would be only operating with the distillation column, this constraint here, which is the distillation column constraint. Here is the reactor constraint, which says that you can't have more than 2 tons going through the reactor. And so if the optimum had been over here, then the slack variable for the reactor would have been non-zero. If you operated here, let's have a look at that. This is where, if the optimum were here, this is where where x1 equals 0 and x2 equals 1. Right, now we can go on to our equations. And I must use the arrow. Oh, geez, what happened there? Oh, that's the end of the slides. Okay. So x1 was 0, x2 equals 1, and x4 equals 0. So that equals 1. Now, if we look at so that is against this constraint, because x4 equals 0. If we had x1 equals 0 and x2 equals 1, then x4 will have to be 0. Now, if we look at the other constraint, the reactor constraint, x1 equals 0, x2 equals 1, and therefore x3 will have to equal 1 so that we can get the equality. And so if the optimum lay over there where x1 equals 0, x2 equals 1, then this x3, this slack variable, would be non-zero, which means that this constraint is not being exercised. We are, as soon as that is non-zero, we are not against that constraint. The optimum is not lying against that constraint. Okay, so that's essentially what it means from a feeling point of view, not so much mathematical. So yeah, that's what slack variables are. They just tell you whether you're against that constraint. So that slack variable will tell you whether, if that's non-zero, it'll tell you that you're not against that constraint. And if this one is non-zero, it'll tell you you're not against this constraint. Right, let's see. So is the goal to minimize? No, the goal is to minimize that objective function. or maximize the objective function in this case, because we want the objective function has been defined as there it is. It's defined as profit. So if you make an equal amount of A as you make of B, the amount of profit you get is 3 times more due to whatever tonnage you're making of B. And when you find that optimum, in other words, when you find the maximum value of F, then it may be that some of these slack variables are non-zero, and it just gives you an indication which of these equations, which of these constraints, essentially, well, there are constraints, which of these constraints is still operable, or whether you're against that constraint or whether you're not against the constraint. If you're against the constraint, the slack variable is 0. If you're not against the constraint, the slack variable is non-zero. But that's it. You guys have done this before in matric. You might have forgotten, how do you apply what we've learned in a practical sense? Okay, in Excel, you can go and have a look at linear programming. There's a linear programming tool in Excel, and there you can define your objective function. You can define all of your constraints, and press a button, and Excel will find the answers. In a practical sense, the reason you would use linear programming is because it solves so quickly. These days, computers are so fast. It's fairly irrelevant whether it's a linear programming problem or not. As long as it's continuous, you can find the solution quite easy. Now, when I started working at the university, which was 25 years ago or so, NatRef, the petrol refinery, was using linear programming to determine how much 93 octane, 95 octane, how much diesel, how much jet fuel, how much, all of those things, of course, are production rates, just like we've got over here. And then they can operate their catalytic cracker at different temperatures to ensure that you get more jet fuel, less petrol, and so on. And then you also have your octane enhancing unit operations, and you can tweak those ones so that you get more high octane fuel and less low octane fuel. And that whole thing was a linear programming problem. And in those days, it took in the order of hours to run that program, and that would define their production goals for the day. So certainly in the old days, you can get really big problems. You can solve really big problems with linear programming, but these days computers are fast enough that it doesn't really matter. Okay, so Luca, that's the answer. Is you can use Excel on a practical level on a PC. It's as easy as that. Right. So now, should we go on to? No, let's wait for the TUT. So the TUT will be after the design period, the design lecture. The design lecture at 12:30. I must still create a lecture on Blackboard. In that lecture, we'll simply be trying to sort out the groups. So I will put the the group part of Blackboard on the screen, and I'll be able to delete and adjust. Can we use Excel for the assignment as well? No, you can't, because the assignment problem is a nonlinear programming, is a nonlinear problem. So you've had a look at that assignment. You can see that as soon as you change the flow rate of water, that's not going to affect the flow rate of the methanol product linearly. So if you double the amount of water that you put in, you're not going to double the you're not going to be doubling the, or even it's not going to be proportional. So that's definitely not a linear problem that I gave you. All right, so let's call it a day there, and I'll see you in design project at 12:30.